Hi, in this video, we want to talk about resampling methods in statistics. All right, so what are resampling methods? All right, so after I've collected my data, I have my data in my hand, I'm working with it, I'm looking at it, I want to sample from that collection of data to get more information. That is the big idea of resampling methods, is that I already have my data and I want to sample from it so that I can get more information than I had previously. Now, something that's very nice about the resampling methods is that we make very few assumptions about what's going on. Now, these can be very computationally intensive. They're not a good fit for large data sets frequently, but we can really stretch out our data when we use these techniques. All right, so resampling is a collection of methods in statistics that involves the creation of repeated samples from our observed data, with the purpose of evaluating some characteristic or metric of the original sample, trying to get more information out. These techniques are essential tools for modern data analysis, particularly useful in situations where the theoretical distribution of a statistic is complicated or unknown. All right, so we're going to talk about four resampling techniques in this video: bootstrapping, permutation tests or exact tests, jackknife, and cross-validation. So bootstrapping, we're going to sample our data with replacements. And so if I have 1,000 observations, I'm going to sample with replacements 1,000 times. I'm going to calculate whatever it is I'm interested in. And then I'm going to repeat this over and over and over until I have an empirical distribution of the item that I'm interested in. And then I compare that to my standard sample statistic. Permutation tests, what we're going to do is we're going to shuffle some aspect of our data so that we can compare. So let's say I had male and female, and I wanted to compare IQ. Well, after I have my data, to see if there's a difference, what I could do, I could leave IQ alone, but shuffle the male and female aspect in my data set, and then calculate as if that was the correct true data. Do that repeatedly over and over and over, I get a distribution. Jackknife, what I'm going to do, if I have 100 observations, one at a time, I'm going to remove an observation, calculate the statistic of interest, then I put it back, I go to the next one, I remove the second observation, calculate the statistic of interest, put the second observation back, third, take it out, and I keep on doing this. I pull out one observation each time once, and then I compute the statistic of interest in times, and then compare that to the regular calculation. And then for cross-validation, I'm going to break up my data into train and validation data, but I'm going to do this repeatedly with k-folds, and I'm going to use this to evaluate the accuracy of a predictive analytics model. So resampling methods make very few assumptions about our data compared to the traditional methods, and can be applied in a wide variety of situations, such as estimation, hypothesis testing, and model selection and model tuning. All right, so some big heavy hitters packages for this purpose are going to be the boot package, also bootstrap package, the rsample package, and coin. And just like in other videos, we're going to use the MT-CARS dataset just because it is a convenient one, it's familiar, and it's one that's easy to grab. All right, so first thing I want to talk about before we get any deeper is when to use resampling methods. All right, so resampling methods come into play in a wide variety of situations. So first one is when we're going to be estimating the sampling distribution. The bootstrapping method is ideal when you want to estimate the sampling distribution of a statistic without making any strong assumptions about the population. Now, from your stat theory class, if I have a theoretical assumption about what's going on, I can use a pencil and paper mathematics to get a deeper understanding of what's going on. But what if you don't know what the assumptions are to use. Well, if you don't trust the assumptions you would be using, bootstrapping comes in and fills the gap. So bootstrapping can estimate the variability or uncertainty of a sample statistic, such as mean, median, proportion, or a regression coefficients. And so something that's nice about this, that with any statistic possible, I can get a distribution built up based off of my observed data. All right, and so here we're interested in taking an average. If I want the distribution of the average, I can use the boot function to do this. And it'll work out what the original is, estimate my bias, and give me a standard error. Very nice. Now for hypothesis testing, permutation tests are a non-parametric method that makes very few assumptions about the data. This makes them particularly useful when the assumptions of classical statistics such as t-test or ANOVA don't hold. They can be used to test the null hypothesis under virtually any experimental situation. All right, so here we're going to be using the coin package, and we're going to just do a one-way test. So I have automatic transmission, yes or no, and we want to see, does it look like there's a difference in miles per gallon based off of automatic transmissions or manual transmission. Now, these are for older cars. Cars have changed a lot since this data set was built up. So I would not say that the results here generalize to today. All right, so something I want to point out is that in the coin package, it wants things to be a factor to be able to run this. If you have a different format in here, it'll kick an error back at you. All right, and so here we have a very small p-value, so we conclude that there is a difference going on. Now, what is that difference? We have to dig in deeper and figure that out. Now, for bias and variance estimation, jackknife method is the go-to for bias and variance of a sample estimator. It is particularly useful when the sample size is small. So one of the things I like about jackknife and bootstrapping is that when I have a pretty small data set, it gives me some tools to work with instead of making assumptions. And so here we're going to use the bootstrap package, the jackknife function. I specify the data I'm interested in and the function of computation, and it'll take care of it for me. And so this pulls one data point out, calculate, and then switch the data point that's pulled out, recalculate, do that over and over and over. And so here we can see the jack values are the values from pulling them out one at a time. Looks like we don't have any bias, and here's our standard error. Now for model selection and validation, the go-to way is cross-validation. For this is a very robust technique for estimating the performance of a model on independent data and for selecting the best model. It's commonly used in machine learning to tune hyperparameters. I used this last week, by the way, at work. All right, so what we're going to do, we're going to chop up our data into K subsets. And what I'm going to do, whenever I get to a subset, I'm going to use that as validation. I'm going to use everything else as training data. Typically, we do 5 or 10. Me personally, I like twofold cross-validation. I do repeated twofold cross-validation. That's my preference. I like to have completely distinct data sets because the training doesn't, there's overlap in the training sets for larger than 2. And so here we can get our mean squared error of our predictions by doing this. And so when I have these 10 folds, I'm going to end up having 10 mean squares errors, and then I'm going to take the average of those mean squares errors. Let's go a little bit deeper into bootstrapping. Bootstrapping is a powerful computer-intensive method used for assessing the accuracy of a sample estimate. It falls under the category of resampling techniques because it works to repeatedly sample with replacement from our observed data. The process generates a large number of bootstrap samples, each of which is used to calculate the statistic of interest. The resulting distribution of these calculated statistics is an empirical approximation of the sampling distribution. So here is the bootstrap procedure. First, I'm going to draw in observation with replacement from the original observed data. This is known as my bootstrap sample. I'm going to calculate the statistic of interest from the bootstrap sample, and I'm going to repeat 1, 2 over and over and over and over. And then I'm going to have an empirical distribution of the statistic of interest. And so this is nice because I have no theoretical assumptions about the statistic. Everything's empirical. Now, if I have a large data set, this can take a while to compute. Now, for us, we're just going to use the boot function to knock this out. I specify the data. I specify the function I'm interested in. And I specify how many bootstrap samples I want. And then inside the boot package, we have a lot of functions to extract stuff. Here, I just chose to do a confidence interval. All right, so there are several bootstrap methods. First one is non-parametric bootstrap. That's the one I just described. There's also parametric bootstrap. So let's say I have my data, specifically like I have a very small data set, and I have enough to estimate the parameters of assumed distribution, but I don't have really that much data at all. So what I could do is if I have I could estimate, let's say, the mean and standard deviation of the population using the data, and then I'll fill it in with an assumed distribution, let's say normal, and then I'll use those 2 parameters I estimated, and I'm going to use random number generation using the assumed distribution and the calculated parameters to generate a new complete data set to get a more complete picture of what's going on. Smooth bootstrapping does kind of like a combination of non-parametric and parametric bootstrapping. And so here's an example of parametric bootstrapping. I assume that I have the normal distribution. I estimate the parameters of the normal distribution from my data, and then I generate new data using the parameters I estimated and my assumed distribution, and then I calculate the statistic of interest. And I can do this over and over and over to get a distribution of the resulting statistic. Now, the next one I want to talk about are permutation tests or exact tests. And so here, what we're going to do is we're going to shuffle, we're going to permute the grouping variable that I have, and then run my hypothesis test as if that was the original data. Doing this repeatedly gives me a distribution. I compare my original data results before permuting to the distribution I get for the statistic. So I'm going to calculate the test statistic from the observed data. I'm going to repeatedly shuffle the labels of the observed data and calculate the test statistic for each permutation. And then the p-value will be calculated as a proportion of permuted data sets for which the test statistic is at least that extreme. So this makes minimal assumptions about the data and can be applied to many different data types and data situations. And we're going to use the coin package for this. Once again, we're going to need to make sure that we have a factor for our grouping variable. And so here we get, small p-value. I reject the null hypothesis. I believe that there is a difference. Now, virtually any hypothesis test that you can think of, we can run a permutation test for, as long as we have groups involved partitioning the data. Now, jackknife, this is where I remove one data point, calculate, do that repeatedly over and over compared to the original full data set statistic. So what I'm going to do, I'm going to create n new samples. by removing one data point at a time. I'm going to calculate the statistic of interest, and then I'm going to get my biased estimate by taking the difference between my regular sample statistic and then the jackknife average and multiply it by n-1. Now, this has a little bit of bias to it, so there is a correction term to it that you can look up elsewhere. I wanted to keep it simple for this purpose. Now, the jackknife estimate of variance is just given right here. And so this is like a leave one out sample variance estimate. And to perform this, we're going to use the bootstrap function with the the bootstrap package, the jackknife function. There are some other uses of jackknife. We can use jackknife to estimate the degrees of freedom of a statistic. So there are more complicated testing situations where it's not really clear what the degrees of freedom really are. Jackknife can figure that out for us. And model selection and regularization, sometimes tuning parameters, it can be difficult and it's not always clear what we should take as the value. Jackknife can help us find good solid estimates. Now, the last one I want to talk about is cross-validation. So cross-validation, I'm going to divide my data set into K subsets of the data. So this is a partitioning of the data. Each observation is in exactly one fold. I'm going to build my model on all but one of the folds. I'm going to do that repeatedly. So if I have 10 folds, I'm going to take all but one of the folds. Let's say I get rid of this one. I'm going to use 9 folds, build my model. And then I'm going to use that one that I pulled out as my validation set. I'm going to repeat that 10 times. So if I do 10-fold cross-validation, I have 10 models being built. And then I take the average of whatever evaluation I'm going to be using for it. So I could be doing mean square errors, mean absolute error. I could be doing, area under the curve. I could be looking at model accuracy, anything like that. And so this is very flexible, very powerful, but it has some limitations in that this is computationally exhaustive. And this can take a long time when you have bigger data sets. Now, we do have some variations on cross-validation. So first one is to stratify our cross-validation. So let's say I have a variable that I know is important and it's categorical. Well, what I could do is I could make sure that I have kind of an equal representation. So let's say my target variable is like a binary variable. I could make sure that each of my folds have approximately the same proportion of every category. And so that would be stratifying my data. I can also do this for a predictor variable if I knew it was important. Now we can also do leave one out cross-validation. So here I'm doing cross-validation within folds, where n is the number of data points I have. Now this can take a long time to compute if I am doing a machine learning model. Regular linear regression has a formula that makes this super fast. Now, the one that I like the most is repeated k-fold cross-validation. I like this one. I like to do repeated 2-fold cross-validation. I find that it's very reliable. I like it. Now, time series cross-validation, this one, what we're doing here is that my folds are chunks of time. My folds are because everything that we've talked about so far in cross-validation is that we have independence between our observations. Since we have independence between our observations, and in this buildup, it's not applicable to time series. So what we're going to do for time series cross-validation, I'm going to chop up regions for my validation sets. All right, so resampling methods, the ones that we've talked about are bootstrapping, permutation tests, jackknife, and cross-validation. These are powerful tools in statistics and predictive modeling. They're flexible, they're robust, and they're great for validating models testing hypotheses, and gaining a deeper insight into our estimations. Each of these methods has strengths and limitations, and we need to consider that before we make our decision on what we're going to do. Fortunately, R is really rich in these techniques. We can really get a lot out of our data whenever we're using R. R just delivers on this front. All right, and here are the homework problems. All right, that's all I've got for you. Life is short. Do math.